Greetings! Today we will learn something about the so-called Yao principle. Now, what is this? It's a tool to prove lower bounds. Lower bounds for the best possible randomized online algorithm for a given problem. Randomized online algorithm. It's for a given problem. Now, why? How does this work? So, we know that by the Loomis theorem and the fundamental theorem of game theory, that if I'm just taking the maximum over all the possible probability distributions P and take the minimum, but this time only for the unit vectors, we even used this thing a couple of times. This is the same as taking the minima in Q of the maxima of EI CQT. Now that's great. What's this? On the right hand side, just remember, this is, if you fix the Q, then taking the maximum of this expression will give you the maximum entry of a row in this vector CQT, which is just the worst possible ratio you can get with your randomized algorithm. So this expression, taking the minimum as well into account, is the best possible competitive ratio of a randomized algorithm. We've discussed this earlier, randomized algorithm. And a lower bound means that I just want to prove that this is larger than something. And here there is a maximum operator. So if I just choose an arbitrary P, then I can of course compute, say P0, then I can of course, if I'm lucky, I can of course compute this minimum P, C, E, J, T, P0 say, and this will be a lower bound for the maximum. So since of course if I'm here, I'm taking the maximum operator over all the possible this probability distributions, then for an arbitrary probability distribution it can be either the same or smaller one for any probability distribution P0. And the important part is this: the minimum is a lower bound of the competitive ratio of the best possible online algorithm. What does this mean? So this here is P0, means this is a randomized input at this point. So this is a randomized input. It's a randomized input given by P0. And the minimum is just the best possible deterministic algorithm against this specific randomized input. So it's the best possible deterministic algorithm against this specific input. So this algorithm can be worse for other inputs, but here this expression means that I first fix the P0, then I choose one specific deterministic algorithm which attains the minimum. And this expression will yield the lower bound. Now, how we do this? For example, if we have the ski rental problem, of course, the ski rental problem, consider the following randomized input. So randomized input for the ski rental problem so it's just like with 1/2 probability. So randomized input is just a distribution over all a set of inputs, so I'm just giving you with 1/2 probability, say B half snowy days. And with another 1/2 probability, I will give you, say, 1/2 B snowy days. Now the important thing is that if here, when we apply the Yao principle, we only have to take deterministic algorithms against this particular input. So we just have to decide, we just have to check how a deterministic algorithm can respond to these inputs. Also note that here this guy is a prefix of this guy. And this is the way how can we exploit the fact that a deterministic algorithm is here to be studied, because the output of the first half, which is just so the output for this will be the prefix of the output of that, because this guy is the prefix of that guy. So if I'm having a deterministic algorithm, then the output, the response sequence generated on this input, will be also a prefix of the output sequence generated for this input. So that's what we exploit, and because of this, it's enough to check the output sequence of this guy here. So it's always enough to check the possible response sequences so it's a possible response sequences tau, say 2. Let's just denote this guy by sigma 1 and this guy by sigma 2. I'm underlying just to indicate that these are vectors, input vectors, and tau 2 for sigma 2, and this determines the response sequence. For the shorter input, because the shorter input is a prefix of the longer input. So this determines this step 1, and we just have to compute what. So with 1/2 probability, the algorithms will just output, say, tau 2 on sigma 2, and we just have to divide as usual. So with 1/2 probability, I'm getting this output, and this would be the optimum. And in 1/2 probability, I'm just getting the sigma 1 input, on which I'm outputting tau 1, on which the optimum would be opt of sigma 1. Yeah. So in general, if you apply the Yao principle, you are ending up usually with a formula like this. You can have more terms. So for example, if I would also consider with some probability, say B, and not only these two cases. And of course, you don't always have the 1/2, but an arbitrary thing, but this is just the expected competitive ratio of the algorithm on this particular input. Now in this case, sigma 1 was b divided by 2, so opt sigma 1 is just b over 2, and here sigma 2 was 1/2 b snowy days, which means that now the minimum of n and b is just simply b. Yeah, good. So that's fine. So basically I will end up with 1/2 b's times the cost of tau 2 plus, so I'm dividing by b over 2, these two, I guess these will cancel out, plus 1/b, the cost of the first output. Okay. And I just have to minimize this. Why? Because here in the formula there is the minimum operator, right? So that's why I have to choose the best possible, well, deterministic response. Now, as always, as almost always, we are doing here a case analysis, which is okay, so let's do a case analysis on tau 2. So there is an option that the algorithm which we choose is just always renting for these phi over 2 1/2 b days. So if the algorithm it just rents for all the days, for each of the days, then the cost for tau 2 will be, well, it's derivative b's, and the cost of tau 1 is, as there were b over 2 snowy days, it will be b over 2. Then we are just plugging this into the formula which we computed. So if the algorithm does this, then it will be 1/2b times times 3 over 2 b's plus 1 over b times b over 2. Oh, how convenient, so it just cancels out, and it will be 3 over 4 plus 1 over 2, which is 5 over 4. Okay, so this means that on this randomized input, if a deterministic algorithm just keeps renting and renting and renting, then it will have a ratio of 5 over 4 on this particular randomized input. Now, there are other options. So, for example, if the algorithm chooses to buys on the jth day, then there are several subcases. So, if the algorithm buys before, or maybe on the first checkpoint, and then what happens? Then the algorithm will spend, of course, j minus 1 plus b amount of money, because for j minus 1 day it just rents, and then eventually it will buy, and this is the same cost as on the first prefix of the input, because j is at most b over 2, so the algorithm will already buy the skis on the jth day in the first input in the sigma 1. Now for this, if I'm just plugging in this value to the formula I got before, so it's, in this case, it will be 1 over 2 b's times j minus 1 plus b plus 1 over b, the same thing, plus b, and this is, so since j is at least 1, this is at least 1 over 2b times b, because this guy here is at least 0, right? So I'm just discarding this part, plus 1 over b, same thing. Now this is again conveniently cancelling out, so this is just 1/2 plus 1, which is 3 over 2. Now this is worse than before, so it says that if the algorithm buys the skis early, so just before the b-half day approaches, then its ratio will be 3 over 4, 3 over 2, which is larger than the previous 5 over 4 which we got earlier. Now the second case is that if the algorithm buys on the jth day, but it's just after the first checkpoint. Now in that case, again, the cost of the algorithm on the whole input is just g minus 1 plus b. But the cost of the algorithm's output on the first prefix of the input is just because of this here, is just keeps renting on the first prefix, right? Because the first prefix is just b-half long. So the cost of the algorithm is b-half in this case. And if I'm just plugging in again the values, well, it will be 1 over 2b times, I have to check which was the 1 over 2b, so the 1 over 2b was paired with the cost of the c, of the longer input, so it's j minus 1 plus b plus 1 over b times b over 2. Yeah, that's great. And that's not so great, but now again, if I'm just computing the minimum, it's enough just to have some bound that is greater than something, and here we can use that j is larger than b half. So j minus 1 is larger or equal to b half. So this is just large, or at least as large as 1 over 2b times b half plus b, plus I'm already cancelled these terms, so it's 1 half. And then, okay, so I can just divide by b here and multiply by b there, so it's just 1 half times 1 half plus 1 plus 1 half. Oh, okay, great. So this is, well, this is a 3 halves, so this guy here is 3 over 4 plus 1 half, which is again 5 over 4. So in this case, the algorithm's competitive ratio is at least 5 over 4. In that case, it was at least 3 over 2. And in this case, it was exactly 5 over 4. So right now I'm able to compute the minimum. In general, I will have some bound, a lower bound for the minimum. So the minimum means that it's at least 5 over 4. So what have we done? This means that the best possible online algorithm has a ratio of at least 5 over 4 on this particular input, which, applying the Yao principle here, we just computed that for this case 5 over 4 is a lower bound than the minimum of the maxima of this AI CQT. And this guy here is the best possible competitive ratio for randomized algorithm. So this means that there is no randomized online algorithm for the ski rental problem. With a competitive ratio smaller, strictly smaller than 5 over 4. So this means that 1.25 is a bound under which we cannot go even with randomized algorithms. So basically this is how we use the so-called Yao principle. We just choose some input vector, some randomized input vector, and then we just compute all the cases how the algorithm, the deterministic algorithm, can respond. In practice, we are just writing up some probability distribution of the prefixes of one specific fixed input. In this case, there was the longest input of 3 over 2 b's, and one of the prefixes of this guy is 1 half b, and we just have to consider all the possible output sequences for the longer guy, and it will determine the output for the shorter guy. And in general, we can do this. So for example, we will see some more examples in some next part of the series for the scheduling problem as well, but first we will have to learn something about the scheduling problem in the next video. Till then, bye bye.